Hello everyone, I welcome you all to the Digital Signal Processing Laboratory. The course code is 21EEL66. I am Swapna H, Assistant Professor, Department of EEE, ATME College of Engineering, Mysore. So let us look into the experiment, generation of different signals in both continuous and discrete time domain. The objective of this experiment is to learn the generation of various signals such as unit impulse, unit step, ramp, and sine signal in continuous and also in discrete time domains. The software what we use for this to conduct the experiment, it is GNU Octave GUI. So let us first understand the theoretic concepts of this various types of signals. So the first one is unit impulse signal. It is basically a narrow pulse obtained at time t equal to 0. With an area of 1 denoted by delta of t. So mathematical expression for this is indicated as delta of t equal to 1 at time t equal to 0, and for all other values of t the amplitude of delta t will be 0. So whereas in unit step signal it is also called as Heaviside step function, which we normally denote it by u of t. So mathematically u of t is expressed as equal to 1 for the time t greater than or equal to 0, and for all other values of time t where t less than 0, the amplitude of u of t will be 0. So further we have ramp signal. It is a function increasingly linear with time, so which we denote by r of t. Mathematically r of t is equal to t for t values greater than or equal to 0, and it is 0 for t less than 0. So similarly we have sinusoidal signal. It's a type of continuous time signal that varies sinusoidally with time. So it's characterized by a periodic waveform with a fixed frequency, amplitude and phase angle. So mathematically we express this sine signal as x of t equal to a into sine of omega t plus phi, where this a is nothing but an amplitude, omega is an angular frequency, and phi is the phase angle. So let us look into the program for generation of unit impulse signal. So initially we always start with the clear all command, which will erase all the previous data stored in the command window and also in the history. So then followed by we'll declare the values for n and x, which will indicate the number of samples for which we are generating the signal and for what range of the time duration we are generating the signal. So next we have y, which is indicating the mathematical expression of unit impulse, where the value of signal will be indicated only at t equal to 0, and for all other values it has to become 0. So once we declare all this n, x and y, so in order to plot the signal we need to have this command stem of x comma y, where time duration versus the amplitude will be considered. So followed by labeling of the graphical representation. So with x label as time, y label as amplitude, and title for this graphical representation is unit impulse signal. So the output would be looking like this. So once the program has been saved and run, so it will ask us to enter the number of samples for which we have to generate the signal. So let us take it as 5. So this is the graphical representation of the unit impulse signal. The range we can observe here, it is from -5 to +5, and at n equal to 0, so we have an unit impulse amplitude as 1. Next we look into the next unit step signal. Similarly we'll declare the variables n for number of samples for which the step signal has to be generated, and for the time duration t, and also the amplitude as per the mathematical expression. The step signal should start from t equal to 0, and for greater than equal to 0 the amplitude should be 1, and for t less than 0 the amplitude should be 0. So next, once we declare this n, t and y, so to represent it graphically, we need to have this command called plot. So wherein we will be taking the x-axis with the time duration and y-axis with the amplitude. Followed by labeling of time, amplitude and the title. So the subplot will give us the multiple figures into a single window. So since the objective is to represent a signal in both continuous and time domain, so in order to have a signal for continuous, we need to use this command as plot, whereas for the discrete time signal, we need to have a command called stem. So in order to display both the signals in a single window, so we need to use this command called subplot, where it will create two rows, one column. The first figure, it will be indicating the continuous time signal, whereas subplot 2, 1, 2, where two rows, first column, the second figure would be representing the discrete time signal, which has been given with the command stem t, y, followed by labeling of the signal graph. So once we run the program, the output would look like this. For the sample values of 5, this is the graph we obtained. So the first figure, where two rows, first column, the first figure is indicating the continuous unit step signal, whereas the second figure is indicating the discrete kind of step signal. Next we have ramp signal. So followed by similar way, we are going to declare the variables here for number of samples to be considered and for the coefficient a. Then we are going to declare the time duration and the amplitude. Since the ramp signal is a linear function, so y is equal to a into t. So a is indicating the coefficient and n here is nothing but the number of samples for which the ramp signal has to be generated. Followed by, so in order to have a graphical representation, we need to use this command figure. Then again, in this, to have for both continuous and discrete time signal, we are dividing it with a command by subplot, where both the signals will be visualized at a time in a single window. So plot t, y will indicate the continuous ramp signal, followed by labeling of x, y axis and title as continuous ramp signal. Followed by, we have a subplot, that is the second figure with a discrete ramp signal. The command we use is stem t, y. So followed by labeling of the second figure. So this is how the output we will get. The command window, it will ask us to enter the number of samples for which the signal has to be generated. So it is 5, n is 5, and the coefficient value taken as 2. So this is the figure we get. So the first figure is a continuous ramp signal. So it's linear in nature, so across time t and the amplitude. So whereas the second figure is indicating the discrete ramp signal, where we get the signals only at the discrete instant of time. Next we have sine signal. So in order to generate a sinusoidal signal, we need to declare with the frequency. Since it's a periodic signal, we need to declare with the frequency for what duration we are taking. So here f we are taking it as 50, followed by the duration from 0 to 0.04. y1 is nothing but the amplitude of the sinusoidal signal. Mathematically, we have an expression sine 2 pi ft. So it is 2 pi, f is the frequency we considered, and t1 is for the time duration. So once we declare with the time and the amplitude, so next the graphical representation with the command plot followed by labeling of the figure. So similarly, we have indicated the time t2 for the range of 0 to 0.08. So as with a new amplitude for the sine wave as y2 sine 2 pi f t2, and this signal we are going to indicate in the form of a discrete time signal. So for that the command we use a stem, so stem t2 y2 following by the labeling of the second figure. So once we run the program, so we'll get the output of this kind. So where the first figure is indicating the continuous time signal, so for the range of time duration of 0 to 0.04, and the second figure from 0 to 0.08. So it is also a sinusoidal signal, but it is at the discrete representation. So now let us run the program in the software Octave and let us verify the output. So first open this Octave software, click on this file, select new script. So here just copy the program what we have discussed so far. So then click on this run and save button. So once we click here, it will ask us to select a path. So create a folder. So in this folder, let us save this file as experiment. So the extension for this file will be .m. So just add directory to the load path. So once it is done, so the program typing and running of the program will be done in editor window. So next to this we have a command window. So we'll click on this. We can see it is popping up with the information of enter the value of n for n number of samples. So let us select it as 5. Enter. So we can see a unit impulse signal which has been generated for the range of 5 samples. Similarly, we'll create one more file with a new script. We'll copy the unit step signal program . Save and run the file. So with the .m extension. So once we run the program, so if you check it in the command window, it is again asking for enter the number of samples n to generate a unit step signal. So let us take it as 5 again. So here we can see the figure with a unit step signal. So here we can observe the first figure as a continuous step signal and the second figure as a discrete step signal. Similarly, we'll come back to the editor window. We'll take up a new script. We'll run the program for the ramp signal generation. Paste it here, save and run. Select the folder path, save a file with the extension .m, add directory to the load path, run the program. So come back to the command window. Again, it's asking for the number of samples for which the ramp signal has to be generated. I'm giving it as 5 and the coefficient will select it as 2. So once we are given with the 2 values, so we can see the figure of ramp signal has been generated. This is a continuous ramp signal and this is a discrete ramp signal. Similarly, so we'll take up one more new script. We'll copy the program for sinusoidal signal generation. So we'll run this program by saving it to the folder. So add directly to the load path. Once it is done, you can see a sinusoidal continuous sine signal has been generated, and also the discrete sinusoidal signal has been generated. So this is how the program can be analyzed and generated with all the different types of elementary signals. Thank you.